Hello and welcome to College Algebra. I'm your instructor, Scott Daugherty, and in this video I'm going to go over some of the material from R1. There are 8 objectives in R1, and in this video I'm going to cover the first of those 8 objectives. Now I will cover the other objectives in another video. So let's start with this first objective in this R1 section, is to identify subsets of the set of real numbers. Okay, and let's start with the definition of a set. So one of the most basic and fundamental ideas in mathematics is this idea of what's called a set. A set is simply a collection of items called elements. And we use these little braces to start and end the collection of items in our set. So for example, you can see here that you have a beginning brace and an ending brace, and inside there you have 3 different items: gold, silver, and bronze. Okay, that is an example of a set. Now in mathematics, we usually don't have sets of real-world items. We usually have sets of numbers. Now, a set that does not contain elements is called the empty set, or sometimes called the null set. And we denote that empty set either by putting the braces here, the beginning braces and the ending braces, with nothing in it, and so that means it's empty, or sometimes we use a little zero with this little line through it. So I think this is the more common notation that is used, a zero with a line through it. Okay, that's known as the empty set. And that simply means that there's nothing in your set. Not even zero is in your set. Nothing is in the set at all. Okay, that's called the empty set. Now, sometimes you'll see this little symbol here. It's called an epsilon symbol. And that means you have an element of a set. So, for example, you can see here 5 is an element of this particular set. Now, if it has a line through it, then it means it's not an element of the set. So 6 is not an element of this set. And oftentimes we're going to use what's called set builder notation. And so you might see something like this. This is called set builder notation. So this is the opening of a set. And so it's the set of all x values. And this little straight line right here is the way mathematicians use the word such that. So that they're lazy and they don't want to write the word such that. So they use this vertical line, and that means such that. Okay, so this is the set. This is the opening of a set of x values such that x is an even number between 0 and 10, and then this is closing the set. That's called set builder notation. Now, of course, if you wanted to, you could write this out explicitly. It's the set of x values where x is an even number between 0 and 10. So you could actually write out what those numbers are, like 2, 4, 6, and 8. Okay, so we also have this idea of what's called a subset. A subset would be parts of a larger set. So for example, you have the set of all numbers. A subset of the set of all numbers would be the set of all even numbers. That's called a subset of the larger set of real numbers. So we do have these things called subsets. Now let's talk about all the different subsets of the set of real numbers. And by the way, we use this little r to denote the set of all real numbers. Okay, so let's talk about the important subsets of the set of real numbers. The first one would be natural numbers, which we denote with this n. And the natural numbers are just simply the numbers starting at 1, and then 2, and then 3, and then 4, and so on. So it starts at 1, and it just continues to go up to the next whole number, 2, 3, 4, 5, 6, and 7, and so on. Okay, whole numbers, the only difference is it starts off at 0 and then goes 1, 2, 3, 4, 5, 6, and so on. And we denote the whole numbers with this W. Now notice that this is a subset of the real numbers, right? The real numbers would be all the numbers. This is just a subset of those. Likewise, this is a subset of real numbers as well. Okay, the integers, which we use a capital Z for, that includes these negative numbers like -1, -2, and -3, as well as the whole numbers 0, 1, 2, 3, 4, 5, and so on. So those are called the integers. Rational numbers are denoted with a Q, and they're the set of values that look like P divided by Q, such that P and Q are integers, elements of integers, and Q is not 0. So what does this mean? Basically, pick any two integers, P and Q, and divide them. And that's what a rational number looks like, as long as Q is not 0. So for example, -6 and 11. So if I took -6 divided by 11, that's an example of a rational number. Now, one way of remembering this is the word rational has the word ratio, and it's simply the ratio of two integers. That's what a rational number is. So think of it as fractions. Anything that can be written as a fraction is called a rational number. Now, in terms of decimals, all terminating and repeating decimals are rational numbers. So if I were to write like 0.71, that's really the same as 71 divided by 100. And so you can see that fits this idea of taking an integer and dividing it by another integer. So 0.71 is really the ratio of 71 to 100, or 71 divided by 100. And so that's really a rational number. This is also true for repeating decimals. Like if you had, this right here, 0.6 with a bar, means that the 6 continues to repeat forever. And so if you have a repeating decimals can also be written as a ratio of two numbers. In this case, 0.6666666 forever is actually 2 divided by 3. And you can check that on your calculator. So as long as it continues to repeat, the decimal continues to repeat, it's actually a rational number. Okay, and that leads us to irrational numbers, which we use the letter H for. Irrational numbers are real numbers that cannot be written as a ratio of integers. In other words, they're not rational numbers. And there are some examples of this. Pi is not a rational number, so it's irrational. You cannot write pi as the ratio of two integers. Likewise, the square root of 2 cannot be written as the ratio of two integers, so it's irrational as well. Now, in terms of decimals, if you have a decimal and it does not terminate, so it never stops, and it never repeats itself, then that means it's an irrational number. Okay, any decimal that terminates and stops, you can always write that as a ratio of two integers, and so it's rational, like 0.71 stops. And so that can be written as 71 divided by 100. And so that's a rational number. But let's say this continued on and on and on, and it never stopped. So that's non-terminating. As long as it doesn't repeat, then it's irrational. Now, if it continues to repeat like this does, this is non-terminating, but it repeats. This 6 goes on forever and ever, but it's repeating. It's always 6. So if it repeats, it's rational. If it does not repeat and goes on forever, then it's irrational. And so, for example, pi, you can write pi as 3.14159, and it continues on forever, so it's non-terminating. And there is no pattern to those numbers, so you can't say that it repeats at any point. And so that's why pi is irrational. Okay, so this little diagram right here might help you to sort of see how all these numbers fit together. The set of real numbers is the largest set of numbers. And within the set of real numbers, a real number is either irrational or it's rational. In other words, it can either be written as the ratio of two integers or it can't be written as the ratio of two integers. Okay, if it can be written as the ratio of two integers, it's a rational number. And if it can't be written as a ratio of two integers, then it's irrational. So real numbers have to fall into one of those two categories. You're either irrational or you're rational. Now, within the realm of rational numbers, there are different types of rational numbers. Some rational numbers happen to be simply integers. For example, 3. Right? Okay, let's see 3. 3 is a rational number because it's 3 divided by 1. But it's also an integer, right? But then there are some rational numbers that aren't integers. For example, 1/3. 1/3 is not an integer, but 1/3 is a rational number. Okay, and then within the realm of integers is the set of whole numbers. Now, if you go back and look at it, integers are these numbers. Within that set is the set of whole numbers. So whole numbers is a subset of integers. Just the numbers 0, 1, 2, and 3 are the whole numbers. And so that's what this diagram is depicting. Within the realm of integers, some of the integers happen to be whole numbers. For example, 3 is an integer, but it's also a whole number. But -7 is an integer, which is not a whole number. Okay, and then within the realm of whole numbers, some whole numbers happen to be natural numbers, and some aren't. And so you can see that, again, let's go back up here and look at so this is the set of whole numbers, and this is the set of natural numbers. The set of natural numbers is a subset of the set of whole numbers. Okay, for example, 3 is a whole number, and it's also a natural number. But 0 is a whole number that is not a natural number. In fact, most of the whole numbers are natural numbers. The only one that is not a natural number is 0. Okay, but that's what this diagram is trying to depict. The world of whole numbers is a little bit larger than the world of natural numbers. Or in other words, the set of natural numbers is contained within the world of whole numbers. Okay, so that's what this diagram is trying to depict. It's trying to show you the relationship between all of these different types of numbers. Okay, so let's talk about example 1 just to kind of reinforce some of these ideas. A lot of times we use capital letters to denote sets. So capital A in this case denotes this set here, this set of numbers. And we're going to try to determine which elements belong to the following sets. Okay, so let's start with part A. Which of these numbers would be natural numbers? Okay, so if you look through all these, the only one that's a natural number is 11. Now 0 is not a natural number because natural numbers start off at 1 and they go up from there. 1, 2, 3, 4, 5, 6, 7. So the only number in this set A that's a natural number would be 11. So 11 is an element of the natural numbers. What about whole numbers? Well, if you throw whole numbers in there, all right, the only ones that are whole numbers would be 0 and 11, because whole numbers start off at 0 and then they go to 1, 2, 3, 4, 5, 6, 7, and so on. So 0 and 11 are elements of the whole numbers. Okay, integers. Integers are the whole numbers plus all the negative 1, negative 2, negative 3, negative 4, negative 5, right? Those are the integers. So the only ones that would be integers would be 0 and 11 and the negative 16. Okay, rational numbers. Any numbers that can be written as fractions, the ratio of integers. Okay, so now you could include negative 19 over 7. That's a fraction. Including negative 16, 0, and 11, because those can be divided by 1, right? 11 over 1, 0 over 1, negative 16 over 1. Those can be written as fractions. But then you need to look at some of these decimals as well. 0.39 can be written as 39 over 100. Remember, if it's a terminating decimal, then it's a rational number. So that it means 0.444 is also a rational number. It can be written as 444 over 1,000. It terminates, right? Any decimal that terminates is a rational number. Okay, what about 0.83 with the bar on top? That means the 83 continues to repeat. Now, this never stops, so it's non-terminating. It's a non-terminating decimal. But remember, if it repeats, then it's a rational number. And so since this repeats, even though it doesn't terminate, it's still a rational number. So that's also rational. That only leaves square root of 3 and this other number. Square root of 3 is irrational. If you put that into your calculator and take the square root of 3, you'll notice that the decimals there go on forever and they never repeat. And that makes it irrational. Now this number here, it looks like these numbers continue on, and that's what this dot, 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 dot means. It means these numbers never terminate. So this is a non-terminating decimal. The only question is, does it repeat? And if you look at this closely, it's not repeating. You first get like a 2, 0, and then you get a 2, 0, 0, and then you get a 2, 0, 0, 0. That's not repeating. So this is a non-terminating and non-repeating decimal, and that makes it irrational. Okay, so the two numbers here that are irrational are square root of 3 and this number here. All the other ones are rational. And that leads us to the next one. Which ones are irrational? The square root of 3 and this decimal here. Those are elements of the irrationals. Okay, and then the last one is which one of them are real numbers? And of course, all of these are real numbers. Okay, every one of those is a real number. Okay, you may want to practice this. This is a skill practice. You could practice on here, and then below it, it gives you the answers. So you could try that problem. Okay, so that's the first objective. I hope you found this video helpful. In the next video, I will go over this second objective. Thank you for watching. Bye-bye.